Okay, we are going to look at speeds and feeds in this video, and here's the things that we're going to talk about. Sorry, I went by that kind of fast, but we'll get back to those things. First of all, we have to talk about end mills. These are called end mills right here. This is also a end mill, but it's a little different kind. So this guy right here is what's called a center cutting end mill. You can see that it has a tooth that goes right to the middle of the tool, so that makes it a center cutting end mill. This is also a flat surface here, so it will cut a flat pocket. This guy is called a ball end mill. That's why it has this radiused edge, and this also cuts in the center. This guy over here is a non-center cutting end mill. You can see it's got a hole in the middle of it right here, so none of these teeth, which they call flutes, extend to the middle of the end mill. You can plunge with this end mill, you can plunge with this end mill, you cannot plunge with this end mill. This over here is what's called an indexable shell mill. This has replaceable teeth on it. They are probably carbide, and it's much larger in surface diameter than what most standard types of end mills will be. There's also these other tools. These are some other basic cutting tools. This is what's called a countersink drill, or a combination drill and countersink. We have a spotting drill. This is just like any other drill, except it's a lot shorter, which makes it a lot better for drilling holes, because the tip of it will not wander when it touches the material. This is a countersink. This is also a countersink up here. That's why it has this angled surface on it. The countersink here will also cut an angled hole in something. Flutes. Two flute end mill. This is the center cutting one. You can see this is the center right here, this cross of the end mill. One of the teeth extends all the way over to the middle of the end mill, to the center of it, I should say. That makes it a two flute, because there's one here and another one here. That makes it a two flute end mill. They have a lot more room for chip evacuation. You use them on light metals, things like aluminum, plastics also could be used on. The difficulty with these is that they are weak, and they also have a short tool life. This is a 4-flute end mill, 1, 2, 3, 4 flutes. This one is center cutting. You can see two opposing teeth or flutes go to the middle of the tool. So you could plunge with this one. You can plunge with this one. That picture had an end mill, a 4-flute end mill that had a hole in the middle of it right here. That one you cannot plunge with because the teeth don't extend to the middle of the tool. They have more cutting edges, and it has a longer tool life than a 2-flute end mill does. You use these on harder metal, steels, stuff of that nature. They do clog easily in deep cuts though, because they don't have the ability to evacuate the chips as quickly as a 2-flute end mill does. And as I've been mentioning already, center cutting versus non-center cutting. Here is the center cutting end mill. Here is a 4-flute center cutting also, and then this is the 4-flute non-center cutting end mill right here. Different tools. There are different sizes for end mills and different lengths. For instance, this picture has a 1/4-inch end mill. That means this tool will cut a 1/4-inch slot. It's 2 flutes. So if you look at the end of it, you can count how many flutes it is. It's HSS, which stands for high-speed steel. It's a single end mill. In other words, there's only one milling surface on this end mill. If it was a double end mill, they would have another one of these edges or surfaces up here. Mostly used for cutting aluminum. It has a 3/8-inch shank, which is what this is right here. And it is 1 1/4 inches in cutting length. That's the distance from here to here. It's used for these different operations over here: facing, profiling, pockets, slotting, roughing, finishing. It's a general good use end mill for softer materials. Ball end mill, same kind of description thing here. You use these for doing surfaces, slottings, profiling, roughing, and for finishing also. But this will leave a radiused pocket. Countersink, this is a 1/4 inch. That means that this shaft here is a 1/4 inch in diameter. They also use this for deburring. This edge right here would be used to deburr the part. You can also use them for engraving, which is what the tip is for here. As I mentioned, deburring, countersinking, and drilling. And then here is the number 3 combined drill countersink with a 90 degrees. That means that the included angle on here is 90 degrees. And you use those for spot drilling and for engraving. So if you're going to drill a hole in something, typically you put this tool into the cutter holder. You drill in to this, at least this point, and then you can go back and use a regular spotting drill that will follow that littler hole coming from the countersink drill. Spotting drill, as I mentioned, they're shorter, they're sturdier. This one's a 1/4 inch. They come in different sizes also. So cutting speed, excuse me, is the rate of a tool that's measured in surface feet per minute. Spindle speed is the number of revolutions that a tool is going to make per minute, RPMs, and that is made by the cutting tool of a machine. Feed is the distance advanced by the cutting tool along the length of the work for every revolution in the spindle. We are going to learn about calculating spindle speed and feed speeds in this lesson. So here we go. Spindle feeds formula, and it's defined in revolutions per minute. So your calculation when we do that is going to be stated as RPMs, and it's found by dividing the cutting speed of the tool by the circumference of the tool. So here we go. That is the circumference of the tool right there in that little animation. So you're going to take the cutting speed, or the spindle speed, sorry, and we're going to calculate for that. So N is spindle speed, CS is cutting speed, that's what this is, times 12 inches per foot. And then D is diameter. So that is going to be divided by pi times the diameter of a tool. This is what you need to know about when we have cutting speed. So this value right here comes from this chart. And in this chart, it says a couple things. We're going to use aluminum and mild steel for our cutting speeds. This chart has on it the material here on the left and cutting speeds on the right. And you'll notice up here, magnesium, aluminum, look at the numbers, 300, 250, and so on. But the numbers as we go down are decreasing, and this is because this material down here, okay, in the lower part of this chart, is harder than this material is up here. So your cutting speed decreases in that instance. So, question is, what spindle speed should be used to mill aluminum with a 1/2 inch end mill? So here's our formula, and you're going to go to the chart and you're going to find the cutting speed for aluminum, which is 250 feet per minute, times 12 inches per foot, divided by pi times the diameter of the tool. The diameter of the tool here is 1/2 inch. So here's our math for this. So you take 250, multiply that times 12, divide that by the pi times 0.5, and you're going to get 1,910 RPMs. Next one, what spindle speed should be used to mill brass with a 1/4 inch end mill? All right, there's our formula. We're going to go to our cutting speeds, and we find that soft cast iron is 150 surface feet per minute. So let's go back on this. Come on, here we go. Brass and bronze and copper, 150 and 100. So we're going to go back to our problem here. Brass, so that was a cutting speed of 150 feet per minute. So N equals 150 times 12 over pi times 0.25, which is a 1/4 inch right there. You get 2,293 RPMs. Oh, that's right. I forgot. They come to the end of this problem, and then they show you where brass and bronze is on this chart. Silly. Okay. Another calculation that we need to do is for feed rates. So this is the feed rate formula right here, and let's find out what all these are. So F sub M is the feed rate in inches per minute. That's going to be FT right here is the feed in inches per tooth times the revolution. And T is the number of teeth on a tool, how many flutes it has, times the cutting speed, which is the capital N. So here's how you find the recommended tool feeds. This chart, which is in your packet also along with the other chart, is right here. We're going to only use this column for end milling right here. So if we're end milling aluminum, we're going to use 0.005 to 0.010. We always just use the slowest speed when we're doing these things. So aluminum has a speed of 0.005 inches times divided by the tooth times the revolutions. Mild steel down here is 0.002. So that's those are the two values that we're going to use for your questions that we're going to be doing. So you're going to calculate the feed rate for an end mill doing aluminum with 2 flutes and a 1/2 inch high-speed steel end mill. So here's our formula. First thing is we go to our chart and we find aluminum, which is right here. So that should be 0.005. So we're going to use FT is going to be equal to 0.005. Next up, we're going to calculate out our feed rate, which we did already, which comes out to 1910. And then we take and we find the number of teeth, and we're told up here it was a 2 flute end mill, so 2 teeth. So we take 0.005 times 2 times 1910, and you get 19.1 inches per minute. The next problem here is we're going to calculate the feed rate for face milling aluminum with a 4 flute 1/2 inch high-speed steel end mill. So it's a 4 flute 1/2 inch. We're going to do aluminum. So again, we have our milling speed is for aluminum is 250. So we're going to take 250 times 12, pi times divided by pi times 0.5. That gives us 1911. FT is going to be from that chart, and that is going to be for face milling rather than end milling or edge milling. So the number of teeth, NT in this case, is 4 because we have 4 flutes, so that's the number of teeth. And we do our formula. So it's 0.005, which is right here, the FT, times 4 teeth, which comes from up here. And then that's times 1911, which is the cutting speed. And that gives us 38.2 inches per minute. Now there are other things that affect feed rates, how strong the spindle motor is, the condition of the cutting tool. Has it been used for a long time? Is it dull? How deep you're cutting. If you're cutting deeper, you're going to want to slow down. And then the quality of the surface finish. Is it you want a bright shiny finish, so you're going to have to slow down. If you're just getting through the material and removing material, then your finish isn't as necessarily as important, so you speed it up, the feed rate, and what will happen is you'll actually lose some material. And is it what's called roughing versus a finished cut? Again, it's about the same thing as your surface quality up here. And how good the machine is, and your fixturing, how strong that is. Plunge feed rate, there's a whole formula for this, but basically the plunge feed rate is the feed rate that you calculated before divided in half. So when we cut our parts on the mill for the letter blocks, we told you a feed rate of 9 when you're plunging, and it was 18 as we were traveling along. So you take and calculate the feed rate for just regular milling, which in our case was 18, divide that in half, that gave us the plunge rate of 9. So that is the end of our video about feed rates. This is part 1. Part number 2, I'm going to show you how to do the calculations for the problems.